Alright, so for the notes here on 8.3, we are doing what's called the inverse of a matrix, of a square matrix, and there is some parts of the notes that we aren't going to be doing in condensing some of the content in this chapter. But first, before we get into the nuts and bolts of the inverse, we're going to take a look at these problems, which are going to, problems 1 and 2, which are going to be very helpful in terms of understanding what we're trying to do here. So what it says is find AI. We're going to multiply A by I, and if you look at this matrix right here, is called I because it is what is called the identity matrix, and there's a reason it's called the identity matrix. An identity matrix is a matrix where you have ones on the diagonals and every other entry, in this case these two, are zeros. So if we do A times I, we have A11 times A12. A11, A12, A21, and A22. I'm just listing these. That's our first matrix. And if we multiply that by the identity matrix, we'll set that equal, or put the equal sign. Now we go ahead and go through the multiplication. We have a 2 by 2 times a 2 by 2, and as we practice, we know that's going to give us a 2 by 2. So first I'm going to find the A11 term. So that would be first row times first column. So that would be A11 times 1 plus A12 times 0, which would just be A11. So that goes there. Now here we have the 1, 2 term. So I'm going to go row 1, column 2. A11 times 0 plus A12 times 1 will give us A12. Now we want to get this term, which is entry 2, 1, so that's going to be row 2, column 1. Row 2, column 1, that'd be A21 times 1 plus A22 times 0 would just be A21. And then lastly, we have, over here, entry 2, 2, row 2 times column 1, A21 times 0 plus A22 times 1 is just A22. If you look at this matrix is the exact same matrix as that. That is why this is called the identity matrix. Just like 1 is our multiplicative identity for multiplication, when we take this matrix and multiply it by this, it returns out the same. Just like if I take 5 times 1, it gives us 5. So that's our identity matrix. That's going to be relevant in a second here when we look at A times B. If you want to fast forward through this, I am going to go through the details of multiplying these, but if you want to fast forward it, if you're good with matrix multiplication, that's fine. Let's see what happens. We get row 1 times column 1, negative 1 times 1, plus 2 times 1 is 1. And we have row 1 times column 2 is 2 plus negative 2 is 0. Row 2 times column 1 is negative 1 plus 1 is 0. And then row 2 times column 2 is negative 1 times negative 2 is 2, plus negative 1 is 1. So if you look, if we multiply A times B, we end up getting the identity matrix. And if we do B times A, which I will do here, so I'm going to put B here, I put A here, B is 1, negative 2, 1, negative 1. A is negative 1, 2, negative 1, 2, negative 1, negative 1, 1. Okay, so a 2 by 2 times a 2 by 2 gives us a 2 by 2. We go row 1 times column 1, that'd be negative 1 plus 2, which will be 1. Row 1 times column 2 is 2 plus negative 2 is 0. Row 2, column 1, negative 1 plus 1. Let's see if we let's gotta make sure on this. Negative 1 plus 1, yes, is 0. Oops. 0. And then we have row 2 times column 2, that'd be 2 plus negative 1 is 1. So we see in any order, if we do A times B, which is equal to B times A, which is equal to the identity, that tells us, think about two terms that we multiply, two numbers that we multiply and we get 1. Those are reciprocals of each other, and they're also inverse operations, right? So like 5x equals 10, we divide by 5 or multiply by its reciprocal 1/5, inverse operations. So these are considered inverse matrices of each other. So that's going to be relevant to us in terms of solving equations, or solving matrices, actually. We'll be getting into that later. So the reason I mentioned that, so imagine if I have the equation ax equals b, we divide by a on both sides, but in matrices we don't divide. If we think of A as a matrix, X as a matrix equals B, what we could do is multiply A by its inverse matrix. I'm going to give myself space here. I'm going to put the B over here. B like this. Now, if I multiply by the inverse matrix of A, I'm going to call it A inverse. A inverse times A will give us the identity matrix, just like we had A times B. And note, I need to multiply it in the same order. So now those cancel, and we have X equals A inverse B. Note, if I had A inverse multiplied by A on that side, I need to keep this on the left-hand side of B, because matrices do not always commute. They did commute up here in the example of inverse matrices. Inverse matrices commute, but as we saw before, not all matrices commute. So to stay consistent that all matrices don't commute, this A inverse has to be in front of B. So now that gives us a method for solving systems. Like I said, the main goal of this unit is to, one, learn some basic matrix mechanics, inverse determinants, things like that. But also all of these we are going to learn in the context of, for the most part, solving systems. Okay, so inverse of a matrix is defined as AB equals BA, gives us the identity n, and that's talking about n by n square matrices, right? So n by n means 3 by 3, 2 by 2, 3 by 3, 4 by 4, n by n in general. And AB times BA gives us a square identity matrix of an order of that I sub n means of the order n by n. A is called, this is just some terminology, invertible or non-singular if there exists an n by n matrix B that give you the inverse. Meaning, if a matrix has an inverse, it is called an invertible matrix. If it doesn't have one, because there are examples of matrices where you cannot find a matrix times B or a matrix times some other matrix and get an inverse, then those are not invertible, or they are considered singular. So down here, the uniqueness of an inverse matrix, what this is essentially saying is the inverse of A is denoted by A inverse, that's the notation, and there is a unique inverse, meaning if A times B equals I, that B, if A is our original B, there is only one inverse to that matrix. So that is why it is considered unique. Okay, so this part is not in our notes, but this setup right here that we're about to work out is going to move us into what we see in our notes. So let's say I have a matrix here, 1, 4, negative 1, negative 3, and I know there may be some matrix right here which is the inverse, that if I take this matrix times this matrix, that gives us 1, 0, 0, 1. So what we could simply do is say, well, if I go that times that, if I go row 1 times column 1, that gives us entry 1, 1, and we actually have an actual equation. 1 times x1, 1, so it'd be 1, x1, 1, I'm going to put a 1 out front, plus, that will be beneficial just to help us see. Again, we're going row 1 times column 1, so 1 times x1, 1, plus 4 times x2, 1, 4 times x21 equals entry 1, 1, which is 1. Now this is a little different order than I typically go in, but it's going to get me the same variables as this one right here. If I go row 2 times column 1, that'd be row 2 times column 1 will give us entry 2, 1. So if I do that, it'd be negative 1 x11 minus 3 x21 equals 0. That times that plus that times that equals 0. That's what we have right there. So now we have a system right there, and of course we could solve that system. If we now do row 1 times column 2, that would be 1 times x12, 1 times x12, plus 4 times x22, plus 4 times x22, equals, again, that's row 2 times column 1, that'd be entry, that was row 1 times column 2. Row 1 times column 2 will get us entry 2, 2, which is 0. Then, if I do row 2 times column 2, that will give us entry 2, 2. So we have negative 1 x12 minus 3 x22 equals 1. You can always rewind back to this, but this now, this is one system, this is another system. On the next page, it's just going to be written over here. This is the setup. Now, we could, of course, solve these two systems, but our overall goal is to find the inverse of a 3 by 3, and in order to do that, this method that we have here is not going to work for that. But the method we're going to do moving forward for a 2 by 2 is, and what's displayed on the next page will show us how to do a 3 by 3. So let's move over to the next page. So if you look here, this comes from the book. Here was our first system. Here is our second system. So if we take this and go, okay, well, here's a system. We know how to put that into augmented matrix form. That would be 1, 4, negative 1, negative 3, dot, 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 with a 1, 0. Just like what we did on 8.1, take this, put it into augmented matrix. If you take this one and put it into augmented matrix, it gives us that one. Well, imagine, well, if you look first, the coefficient matrices are the same of these. So if we put that there, and then augment all of this together, put a 1, 0 there, and a 0, 1 there, now we have something quite interesting. We now have the augmentation of our original coefficient matrix with the inverse matrix. And if I do row operations to get to here, where we have the inverse matrix on the left, by making this a 0, making this a 1, like so, and then making that a 0, which we haven't done yet. We use row operations after we get a 0 here, and then a 1, then we work back up here to get a 0. I will show you how to do that later. We now have 1, 0, 0, 1, the inverse, the identity over here. This matrix over here ends up being our inverse matrix of our original matrix up here. If I took this matrix, multiply by that, and you could check it if you want, you will end up getting the identity. So, what this tells us, thus by applying what's called Gauss-Jordan elimination to the doubly augmented matrix, we had the original matrix A here, and we augmented it with I, and then getting I over here, this matrix over on the right is our inverse matrix. Down here I have a proof for it. We're not going to go through the proof. That's okay. But we can see it worked in this example, and it works in all examples. So now we have two goals. One, to find the inverse of a 3 by 3. I'm going to go through that. It is virtually the same process we did before in terms of row echelon form. We have to add an extra step into there in terms of getting the 0 up here and it'll be in a 3 by 3, so we're going to have more zeros. That's fine. We'll work through it. And then we will also be using inverse matrices to solve a system after that. So right here, if we have our matrix, a 3 by 3, and we want to find the inverse, there will be one on the test like this. The numbers won't be unmanageable, but this is definitely a relatively tedious process, so we're going to take it step by step. And my suggestion is the more you practice it, the better you will get at it. So 1, 1, negative 6, negative 1, 0, 2, 0, negative 1, 3. We are going to augment it with the identity matrix of a 3 by 3. And for a 3 by 3, again, the identity matrix is 1s on the diagonals and 0s everywhere else. So our goal is we are going to want to get here 1s on the diagonals, 0s down here, and then 0s up here. Before we get 0s up here, we're going to do the same as we've done before with REF, row echelon form, and as we're presenting in this notes, it's also called Gauss-Jordan elimination. That's the star linear combinations that we've done before, just same as the elimination method for systems, except now it's... So first our goal is to get this to 0 and this to 0. To get this to 0, I'm going to take R1 plus the opposite of R2. So R1 plus negative 1 times R2. Then it's going to give us our new R2. Also going to eliminate this by getting this to 0 by multiplying this by 6 and adding it to that. So 6 times R1 plus R3 will get us a new R3. So R1 plus negative R2. 1 plus negative 1 will give us 0. Negative 1 plus 0 gives us negative 1. 0 plus the opposite of this will be positive 1. 1 plus 0 gives us 0, or 1, excuse me. 0 plus negative 1 is negative 1, and 0 plus 0 is 0. Now we do 6 times the first plus the third, so 6 times this plus that will give us 0. 6 times this is negative 6 plus 2 is negative 4. 0 plus 3 is 0. 6 times 1 plus 0 is 6. 0 plus 0, and then 0 plus 1. Now, we do want this to be a positive 1 ultimately, but I'm just going to leave it for now. And we're going to do the one step of eliminating this to 0, just to eliminate some possible confusion. So I'm going to take negative 4 times R2 plus R3, and that will give us our new R3, again to eliminate this term right here, because if I go negative 4 times that will give us positive 4 and add to that to give us 0. Okay, so, excuse me, the first entry is 0. Negative 4 times this would be positive 4 plus negative 4 is 0. Negative 4 times 1 is negative 4 plus 3 is 1. Negative 4 plus 6 is 2. Negative 4 times negative 1 is 4 plus 0 is 4. And then 0 plus negative 1. So now we are very, very close to REF, so we need to make that a positive 1. So I am going to mark it here and just do it on this line. I'm going to go negative times R2 and replace our R2. And then I'm just going to switch all these up and make that a positive 1, and a positive 1, and that one a negative 1. And so now our goal is to make these zeros, and we can think of as we go in this order 0 0 0 to get our REF, to now get these as zeros because we want all of this to be the identity matrix. We're going to do the same thing except flipped. So again, it goes 1 2 3. We're doing the same thing 1 2 3. So if I want to eliminate that one right there, I want to, and note we want to use this bottom line now because we don't want to add a 1 here, so we can't use this up here. So we're going to use our bottom line and work up, almost like a flipping of working down to get these zeros. So I'm going to go negative R3 plus R2, and that will give us our new R2. So when I do that, I'm going negative R3. These two will not affect these two terms, so I can write that right away. 0 1. And now negative R3 plus R2, that will give us a 0 here. And then we need to continue this here. So negative 2 plus negative 1 would be negative 3. Negative 4 plus 1 will give us negative 3. And negative 1 plus 0 will give us negative 1. Sorry, just to note I had some technical errors with this last term here, but as this was 2 4 negative 1, we do negative R3 plus R2 will give us a positive 1 for our last term. So now we already have a 0 up here, which is good. Remember, we want 0 0, now we want 0 here. Well, that seems relatively simple. We need to do this plus that. So that will be R2 plus R1 to give us a new R1. And so when we add up, you think about it adding up, same as adding down, but we're just replacing the top row. 0 plus 1 is 1. 1 plus negative 1 is 0. 0 plus 0 is 0. Negative 3 plus 1 is negative 2. Negative 3 plus 0 is negative 3. And negative 1 plus 0 is negative 1. This now is your identity matrix, and this is your inverse matrix. You simply write as A inverse equals all of this right there. Lastly, we have solving a matrix using that X equals A inverse B. So if we look here, if we write out our coefficient matrix, this will show us how inverse matrices are a way of solving systems. We're going to write this as X, Y, Z. And then this as negative 2, 16, 4. So I knew that the structure of this would work out to this. If we go row 1 times column 1, if you look 4x minus 2y plus 3z equals negative 2, that's our first equation. And we could do that with the other two equations. Now, if we think of this as A, this is x, and this is B, we know we can solve x by doing A inverse B. So if we find the inverse of this, multiply it by B, you will get your solution. When I get back on Monday, I will show you how to find inverses on your calculator. One is a check for your work when you have to do the by hand work for the problem that we did above, as well as if you need to solve a system using this method. Have a good day. I will see you on Monday.